All right, so here comes Biot Savart part 2. Biot Savart law part 2. Now, so we understand that if we have a positive charge q, and if this q moves at speed v, or better yet, let's call this velocity v, then we can use this equation here. B magnetic field equals mu naught over 4 pi q. And then what we have here is velocity v crossed with r. I'm going to use r instead of r hat, and so this is going to be r cubed. We can use this equation to figure out the magnetic field at some location, let's say here, where we want to find magnetic field B here. And we can do it as long as we know the velocity vector, the charge q, and we know the this position vector r that points from charge q to the point where we want to find the magnetic field. Now this works fine for a charge q, single charge q, but what if we have a whole bunch of the charges flowing? In other words, what if there is a current? What if we have current I instead? Right, and so we have a wire, and then let's say you have a wire here, and then through this wire there are a bunch of charges that flow. So you have a bunch of positives that move along this wire. So here's charge q, and this charge q flows in this direction at speed v. Well, it would be convenient if we could take this equation and transform it so that we have something along the lines of the current I. So that instead of this, we could have magnetic field equals that something something, and then there's I here instead of q. And then we could use this new equation here to determine magnetic field around a wire that carries a current, whether the wire is straight or looped into a circle, or whether it's a solenoid, or whether it's something else. So let's see if we can figure this out. Let's clear up the board a little. So here I have this wire, charge q flows along the wire. Suppose I take a small section of that charge. So let's say every second there's a charge q, big Q that flows through, but now I'm only interested in a small section of that big charge, so maybe just this little piece here, and let's call this thing dq. So in that case, I could take this equation, I could say that the magnetic field due to just this dq would be dB equals mu naught over 4 pi. Instead of q, I would have dq times v, speed at which this thing flows, times, well, I'm going to transform this equation. All right, so let's do it this way. This is the same thing as mu naught over 4 pi times q times v cross r hat over r squared. And just the magnitude of the magnetic field would then be mu naught over 4 pi times q times v times the sine of the angle theta times 1, because the magnitude of r hat is 1, divided by r squared. So this would be, I'm going to take this equation and I'll transform it into what I'm going to into something that I can find useful. So anyways, here's v times sine theta divided by r squared. So here's my little dq that flows to the right at speed v. Let's put v here. And then maybe I want to find some magnetic field at some point somewhere here, right? So so this would be my r. So what is the magnetic field at this point due to this little dq, as this dq flows to the right at speed v? This is the equation that I could use. Now dq is the same thing as I dt. If you recall, current I is defined as dq dt, the rate at which the amount of charge changes through a cross-sectional area of a wire, and so from here I end up with this. And so so this is actually how I'm going to introduce current into my Biot Savart equation. And so dB equals mu naught over 4 pi times, instead of dq, I'm going to have I, the current I, times dt times v times the sine of the angle theta divided by r squared. Now, let's look at this here, v dt. So suppose that the charge starts here, my little dq starts here at this point, and then it moves to the right, and it ends up over here, and so it moves through some length L. And it moves at some speed v, constant speed v. Well, it should make sense that v is just going to be, v is distance over time, speed is distance over time, and in this specific case it would be L over t. But since I want to be a bit more accurate, I'm going to write dl dt, just in case the charge flows at a variable, right? Some odd reason. So then I can take this. From here, I'm going to have v dt equals dl, and so I can plug that in here. Now I have dB equals mu naught over 4 pi times I. Now let's see, we want to, all right, so I times dl, where dl is a section of a wire, times the sine of the angle theta over r squared. So you could already use this equation. Make sure we know what it means. I'm going to redraw the picture, and then we'll probably modify this equation into a vector form. But so let's say you have the wire here, and along this wire you have a section of, well, you have a current here that flows. So here's the current I. Let's label this as I. And then what you will do is you're going to consider a small section of this wire. So here's your small section of this wire, and we're going to call this small section dl. So a little bit of the length L. If the whole wire is full L, then dl is a little bit of that length. And you want to now figure out what is the magnetic field at some point here due to this section dl. And here you would have the r vector, and then magnetic field would have some value at this point, and you could calculate it. The dl is also meant to be a vector with points in this direction, same direction as the current I. Right here was your dl, and dl just points from initial position to some final position. So here's your L, you could put vector over it. Here's dl, it points to the right. Here's r, it points this way. The angle theta that you have here, this theta, that angle, different color, that angle is the angle between the two. So you'd have, here you would have the angle theta. Now that means that you can rewrite this in a vector form so that you would have dB equals, and then you have mu naught over 4 pi times, and you could write this as I times, and then you would have dl, the vector, cross r hat over, so this is r hat over r squared. And this is actually the Biot Savart version of the law that you will run into, I think, most frequently in the books. But now I think you should understand what it means. And of course you could rewrite it in this way: mu naught over 4 pi times I times dl. crossed with the actual r vector. If you do that, remember that then you have to divide by r cubed on the bottom, right? Since r is the same thing as r hat. All right, so we have the more general version of the Biot Savart law. That's this one here. Now let's use it to find the find expressions for some magnetic fields. All right, so this is a problem from your worksheet. You should be able to find this problem easily. It's there. I don't remember it's page 2 or page 3, but so we have a current, and here's the current flows to the left. And then the question is find. So what we are to do here is to find the magnetic field produced at these different points. So P1, P2, P3, and P4. Here's the Biot Savart law. And we will use this to solve this problem. So let's state what we have, because we have a couple things here, and that is, so for the given, what I'm going to have is, well, I have the current. I'm going to write that I is 20 amps. And so of course that takes care of I. I know mu naught, this is just a constant, it's 2 pi times 10 to the minus 7th. It's 4 pi times 10 to the minus 7th. And then so what I have to figure out is this expression here. And maybe we'll do, let's do, actually the way I see it is that P1 is in bold, so I think I'm just going to do P1 and I'll leave P2, 3, and 4 for you to figure out. So I'm just going to do P1. All right, so well, let's maybe rewrite this equation, see what we have, and then take it from there. So so far in my given section, I have the current that is 20 amps. So let's rewrite this equation here. And I think I'm going to write it in a in a magnitude form. So dB equals mu naught over 4 pi times 20 for the current times dl times the sine of the angle theta over r squared. So what I need to figure out is the angle here, theta, and remember that the angle theta is, that would be the angle between segment DL. So if I have a little segment DL, if the current points to the left and the segment DL also points to the left, maybe I should draw that. So if the current points to the left, then the segment DL also points to the left. So this is DL. And then that takes care of this piece. And then R, vector R, that's the vector that points from my little DL to the point of interest. And so this would be, this is my vector R, points from DL to the point of interest, in this case to P1. So what I can do is I can figure out R, right? I can figure out this piece R. Let's do that. So R would be a vector that points from the origin to point P. And well, here's what I can do. So the magnitude of R, I'll write it this way, is 3 meters. But then I know that this thing is at an angle of 25 degrees. And so I can draw a picture that looks like this. Here's R. There's magnitudes of 3 here, 3 meters, magnitude of 3 meters. I need to figure out Rx. And I need to figure out Ry, given that this angle here is 25 degrees. And that's easy to do. I should be able to figure out what Rx and Ry are. So let's calculate this, Rx and Ry. So 3 times the cosine of 25. So that I get 2.7. So Rx is 2.7 meters. And then 3 times the sine of 25. Give me 1.3. So this is 1.3 meters. In other words, R, vector R, is going to be, now I have to pay attention to the signs because it points to the left. So negative 2.7, and then the y is going to be 1.3. If I wanted to add z to it, I would just put 0 for z. I don't think there's a need for that, but there's that. And of course, the magnitude of r, I already have that there, so. But I don't actually have to figure all of this out. What I could do is I could just rewrite this here as, so let's take the next step, dB equals mu naught, which is a constant, over 4 pi times 20 times, so the L, let's leave the L here, times the sine of, well, what's the angle between the L and R? It's just 25, so I'm going to write here, this is 25 divided by R, and this is a magnitude, so R has a magnitude of 3. I'm all set except for the segment, this little segment, the L. So let's take it another step, and that is dB equals, let's multiply all of this out. So we get for this 2.82 times 10 to the minus 7th dl. Alright, so this is what I have. Now that I have this here, it's easy to finish the problem in that the segment of the wire, so find the magnetic field produced by 2 centimeters of the wire dl. In other words, what I have here is that the magnetic field that I'm interested in, the magnetic field produced by the segment of the wire that is only 2 centimeters. So you could, if you wanted to, you could try to integrate it, and you'd integrate from 0 to 2 centimeters, but I think it's easy enough to see that this would be 2.82 times 10 to the minus 7th times the segment of the wire dl, which just becomes 2 centimeters, so 0.02 of a meter. And that would do. So then the magnetic field would be just 2 times this divided by 100, so we get 5.64 times 10^2, and then you have to take, so divided by 100, so minus 9, and this would be Teslas. Alright, so I did P1, P2, P3, and P4, that would be for you to do. I only calculated the magnitude of this. As far as the direction is concerned, you could use the right-hand rule to figure this out. So in this specific case, if you were to point your thumb in the direction of the L, you were to use your right hand and point your thumb in the direction of the L here, or the direction of the current, and then curl your fingers, you would find out that the magnetic field points into the page at this location. And so you would have, for the magnetic field direction, you would just put X, because X means into the page. Remember, X is into the page, and that with a circle is out of the page. Okay, and so that's that. Here's a simple problem.